Hi everyone, today we're going to be talking about topic 3.8, representations of solutions. So in the last lecture, I talked a little bit about this natural tendency towards mixing that makes making solutions favorable. And the reason for this is a term that's known as entropy. Now, we're going to cover this a lot more in Unit 9 and talk more about this definition of entropy. But for now, all we need to know is that this is the disorder in a system. And generally, things tend to want to be disordered. And so when we mix solutions, what happens, or whenever we mix a solute into solvent and a solvent, this causes more randomness in the position of molecules, which increases disorder, otherwise known as entropy. And so it's this increase in randomness in this movement that makes mixing favorable. Now, of course, we've talked about this before, but one thing that we can't forget when it comes to solutions is our intermolecular forces, right? Any intermolecular force can be an attraction between a solute and a solvent molecule. It can be between two different solutes. It can be between solvents. It can be between solute and solvent. But all of these intermolecular forces are going to essentially describe whether or not something will dissolve or if it won't dissolve. Now, there's a few important attractions involved when forming a solution that we always need to think about when we think about if something is going to mix, and in any problem that we're thinking about here in solutions. And so we have solute-solute interactions. Right, these are interactions within the solute that you're trying to dissolve, and these must be overcome in order to dissolve something. Right, and so if you have really, really strong interactions that are causing a solute to not want to dissolve, right, it's not going to tend to dissolve because the solute is really attracted to itself. We have solvent-solvent interactions. Right, these are the interactions between the solvent molecules that we want to dissolve the solute in. These must also be overcome to make room for the solute. Right, so if you're trying to add a solute into a solvent, the solvents themselves have to separate from each other to make room for that solute to come in. Now, the final interaction that we need to consider, of course, is solute-solvent interactions. And these occur with mixing. And of course, these help mixing. Right, so the stronger our solute-solvent interactions, the more likely something is to mix. Now, of course, there's a few things that follow naturally here. If solute-solvent interactions are greater than solvent-solvent or solute-solute interactions, then a solution forms. Right? If you have really strong interactions between your solute and solvent, it's going to want to form a solution. If solute-solvent interactions are about equal to solvent-solvent or solute-solute, then again, a solution will form. And really the main reason for this is entropy, right? It's disorder. Generally, things like to be more disordered. If you dissolve your solute in your solvent, despite the fact that those interactions are about equal, it's the fact that it's becoming more disordered, right? That ordered salt, that solid is now dissolving and kind of moving all around in solution. That's a little bit more disordered. It's favorable. Even though they're about equal, it's still more favorable. However, if solute-solvent interactions are weaker, right, less than solute-solute or solvent-solvent, a solution does not form. Right, and so if the molecules in your solute or your atoms in your solute, whatever it may be, are really, really, really strongly attracted to each other, much more so than the solute dissolved in the solvent, then a solution is not going to form from that. Now, we've kind of seen solvation a little bit before when we were talking about ion-dipole interactions. But for example, if you have, right, some sodium chloride crystals dissolved in water, right, you throw in your crystal structure here, your crystal of sodium chloride in water. All right, what's going to happen is that your chloride ions are slowly going to be pulled away by the water as well as the sodium ions. And what will happen is that the slightly positive end of the water, in this case this hydrogen here, is going to be really close to the negative chloride ion. And so actually I'm not even going to draw a delta negative. This is just a straight up negative. Right, those are attracted to each other. And so your chloride ions are going to be pulled away from this crystal structure. The same thing is going to happen with our sodium, right? We have our slightly negative end of water here, this oxygen, and that is going to be attracted to this positive bit here of the sodium ions. And so what will happen eventually is we'll get this situation where each of those ions are completely dissolved. They're hydrated in solution, so you don't have any solid salt in there anymore. Now you just have a solution. Now, of course, I'm sure we've all seen this to some degree before, but we got to remember that like dissolves like. There's a term that we often use in chemistry called miscibility. Right, miscibiliti, miscibility, which describes the ability of two substances to mix. Right, and so these can be two different solvents, these can be two different liquids or a solid and a liquid, but essentially it's the ability for two substances to mix, and the important thing here is without separating. Right, so like oil and water, for example, are not miscible. They don't like mixing together. If you try, they're going to separate. A few points to always remember, and I'm going to write these in blue. Polar solvents dissolve polar solutes. And non-polar solvents dissolve non-polar solutes. Right, you're not going to really have a case where a polar solvent is dissolving a non-polar solute. They don't really like to be around each other. You might have something like an ion-dipole interaction that could help this, but generally, polar solvents like to dissolve polar solutes. Non-polar solvents dissolve non-polar solutes. We're going to see what are known as particulate diagrams coming up quite a lot throughout AP Chemistry, and it's a great way of representing a solution. And so what it'll show you is essentially this little cartoon diagram here or here, which shows you what's in solution as well as a concentration in solution. So in this case, we have, right, 0.20 molar KCl. You can see here, right, because it's KCl, we should have an equal molar, right, 1 mole of K per 1 mole of chloride. And so in our particulate diagram, we should have 1 mole of chloride per 1 mole of K. If we look here, we have 4 Cl minus and we have 4 K plus. And so this is describing the situation where we have 0.2 molar KCl, but then you could say in this other solution of 0.1 molar KCl, you should have half of each. So you should have half the number of chlorides. So in this case, we have 2 Cl minus. You should have half the number of potassium. In this case, we have 2 K+. And so these diagrams will come up very often. You're going to be expected to know how to draw these, but they can be used to describe kind of how much solvent is dissolved, how much solute is dissolved in a solvent, and to represent what's going on in a solution. Right, and so let's do a little bit of practice here. And so here we have a drawing representing a solution of magnesium chloride, MgCl2, a 0.1 molar solution of MgCl2. So it's asking us to draw a particulate diagram of 0.05 molar MgCl2 with the appropriate number of magnesium chloride ions. And so what I do is I draw a circle or a box, whatever you prefer, but I draw some sort of a container essentially. And I look at my diagram here. I have 2 Mg2+, and I have 4 Cl-. If my concentration is half of what I have here, so I should have half the number of ions in my diagram. And so I should have, let me draw this a little bit bigger. I should have 1 Mg2+, and I have 4 Cl- in my 0.1 molar case. And so in this case, I should have 2 Cl-. Right, so I'll have half the ions as before because my concentration is split in half. And I remember that it's MgCl2, so for every 1 magnesium, I should have 2 chlorides. So 1 Mg2+ and 2 Cl-. And so if I'm trying to do a particulate diagram, this is how I would describe the particulate diagram of 0.05 molar MgCl2. And so here's another example of a problem that I might get in trying to when trying to represent a situation using a particle diagram. And so a student mixes a dilute sample of AgNO3, or silver nitrate, it's aqueous, so it's dissolved in solution, with excess NaCl, or sodium chloride, again, aqueous. And so you take 2 solutions, mix them together, and you form AgCl as a solid, right? And so a precipitate forms. And so it's asking us, how could this best be represented in a particulate diagram form? And again, it's telling you AgCl does not readily dissolve in water, meaning that it precipitates. So if I'm thinking about this reaction in general, right, I take AgNO3, which is aqueous, AQ. I take NaCl, which is also aqueous. I put them together in solution. I get AgCl, which is a solid. And because this is a double replacement reaction, I should get NaNO3, sodium nitrate, and this should be aqueous, right? I'm not told in this case that sodium nitrate precipitates, and so we should assume that it's aqueous. If I think about this in terms of ions, I should have Ag+, which is aqueous. I should have NO3-, which is aqueous. I should have Na+, which again is aqueous, right? It's an ion in solution. And I should have Cl- in solution, which is aqueous. And then after the reaction, I have AgCl, right? This is a solid, and so it's not the individual ions when you're in solution. I should still have Na+, because this is aqueous, and I should still have NO3-, again, because it's aqueous. And so if I want to think about this as a particulate diagram, I'm going to draw a box this time. All right, my AgCl, that's a solid, and so it's not going to be floating around in solution. This is just kind of going to be a little blob, right? Something dissolved or undissolved at the bottom of my flask here, right? It's precipitated. It's not in solution. So anytime I have a precipitate, I want to depict it in my particulate diagram like that, just sitting at the bottom of my flask. And so now I need to think about what I have afterwards as well. I have Na+, and I have NO3-, right? So I should have Na+, it's equal, right? I have 1 mole of each in this case, and so I should have NO3-. Maybe I have, right, 3 of each. Right, and so this is what that would kind of look like, but I need to really read this problem carefully. I have excess NaCl, meaning I have more NaCl than is necessary to form my precipitate. And so what'll happen here is at the end, I should still have a little bit of Cl-, right? Because it's excess. I have way more than I need to react. And so I should maybe have a few chloride ions as well. And so in this case, if I'm thinking about this precipitation, I want to show this in a particle diagram. This is what my particle diagram would have. I would have, and I'm going to write this in red, AgCl, solid, undissolved, precipitated at the bottom, And then in solution, I would have some sodium ions, and I would have some nitrate ions, right? And because I'm, again, excess sodium chloride, I may have one more sodium than nitrate. In this case, if you were asked this question, this would award you full points. We'll talk a little bit more about this in class, but for now, that's all. Thanks, guys.